Right, so in this slide, we are going to study the concept of thermal expansion of solids and liquids. Alright, so the principle used here is that objects will expand when they are exposed to higher temperature, right? Or they shrink, okay, when they are exposed to lower temperature, right? So we have expand, okay, object expands when they are exposed to high temperature and shrinks, okay, when they are exposed to low temperature, right? Now basically we have three types of thermal expansion, okay. The object can expand linearly, right? For example, the length, okay, only the length of the object change, okay, due to temperature difference. For example, okay, if initially the object has initial length of L naught, right? So when it is exposed to high temperature, the length increase, right? So meaning we have delta L here, right? And it has been observed that, right, the change in length, okay, is directly proportional to the original length L naught, and it is directly proportional with the change of the temperature, right? Thus, we have one equation, okay, for linear thermal expansion, that is delta L equals to, okay, one coefficient alpha and then L naught delta T. Alright, so alpha is known as a coefficient of thermal expansion, alright, and the unit for alpha is per Celsius, right? Now, what about the two-dimension thermal expansion? Okay, for this case, okay, we know that this is more to change in area. Okay, change in area, as you see in the figure here. All right. So when we expose, okay, the fire, okay, to this object, okay, what happens is that, okay, it will expand. It will be expanded, okay, evenly. All right, evenly. Okay, so the radius will increase, right? So therefore area will also increase, right? So in this case, okay, delta A, the change in area, all right, also directly proportional with the original area, and it is also directly proportional with the change of the temperature, right? Okay, as a result, okay, we may have the same pattern. Okay, the equation here, we have delta A equals to, alright, A naught delta T. Okay, but here, okay, the coefficient here, since we know that okay, area is L times L, alright, so therefore the coefficient here also follows. Okay, so here we have 2 alpha. Okay, but generally we replace 2 alpha with gamma. Okay, gamma A naught delta T. Alright. Okay, how about expansion in 3 dimension? Alright, so this one more to volume. Alright, so the volume of the object change. Okay, when we expose it to temperature difference, right? So we know that volume equals to L times L, right? So with the same pattern as we've discussed for area expansion, here delta V is directly proportional with the initial volume V naught and the change in temperature delta T, right? So therefore, we have delta V equals to 3 alpha, okay, V naught delta T. Alright, so 3 alpha is volume, the coefficient of volume thermal expansion. Alright, and sometimes we replace it with beta. Okay, beta V naught delta T. Alright, so one application of linear thermal expansion, okay, when you have bricks, okay, you combine, when bricks are combined together, alright, so normally we have a gap, okay, between bricks, okay, so the gap here we insert a soft material, okay, so that, okay, when they are exposed to temperature difference, right, when it expand, okay, the bricks doesn't crack, okay, they tak crack begitu banyak, right, because we have a gap inside and soft materials between the gap. Alright, so there will be reduced crack. Okay, now the diagram here shows how, okay, area of the of the object, okay, expand, okay, when it is exposed to the heat, right? Now, table 18.1 shows shows various value of alpha, right? So as you can see here, okay, alpha, it is restricted to solids, right? So for linear thermal expansion, okay, it is more to solids, right? And for apa ni nama ni, gamma and beta, more to liquid and solids, right? So as you can see here, okay, let me choose ordinary glass and pyrex, okay? Okay, because these two are common to us, isn't it? All right. Now in our lab, okay, the glass used is pyrex, okay, so that it does not break easily, isn't it? Okay. For ordinary glass, it can break easily, right? Okay. So why? So you can see the value of alpha here. All right. So for ordinary glass, okay, the value of alpha is 9 times 10 to the power of -6 per Celsius. Okay, untuk pyrex, 3.2, much lesser, isn't it? Alright, so we have that alpha for pyrex is less than alpha than the ordinary glass. Okay, so it shows that, okay, materials that have higher alpha, they can expand easily, right? So thus they break easily, right? So meaning that they cannot withstand higher amount of tension, okay, ataupun external force. Okay, they can break easily because they have higher alpha. So remember, higher alpha, okay, tend to expand more. All right, tend to expand more due to temperature changes. Right. Now, for beta, okay, so this beta, right, where beta equals to, okay, 3 alpha, right, so it is more to liquids and gases, all right, so when you compare the value here, all right, all right, so alcohol, okay, for example, alcohol, okay, nak compare alcohol dengan glycerin, okay, glycerin is one type of oil, isn't it, all right, so meaning, okay, for glycerin, we have 4.85 times 10 to the power of -4. Okay, alcohol is much lower. Alright, so meaning that glycerin can expand more, okay, compared with the alcohol. Alright, okay, so to check your understanding, alright, so quick quiz 18.3. If you are asked to make a very sensitive glass thermometer, which of the following working liquids would you choose? Alright, so kalau nak very sensitive glass thermometer, of course, we are going to choose material that very sensitive to expansion, isn't it? Alright, so compare mercury, alcohol, gasoline, and glycerin. Alright, so you choose, okay, from the table which has a very high beta, isn't it? Alright, so from here, the one that has high beta is gasoline, right? Okay, where we have 9.6 times 10 to the power of -4 compared to the others. All right, so the answer is C. Right, so very sensitive glass thermometer, meaning we are going to choose the one that has higher beta. All right. Okay, next. Two spheres are made of same metal and have the same radius, but one is hollow and the other is solid. Okay, same metal, right? So kalau same metal, okay, they will expand at the same rate, right? They will expand at the same rate, right? So the spheres are taken through the same temperature increase, right? So when they are exposed to higher temperature, they will expand at the same rate. So therefore, the size will be the same, isn't it? Okay, the size will be the same. Okay, so here we can say that the answer is, okay, the solid sphere expands more. No, because they are same material. All right, the hollow sphere expands more. It does not depend whether they are hollow or solid. They expand by the same amount. Yes, okay, because they are made of same material. All right, so the answer is C.